Hello everyone and welcome back. Today we're going to be continuing our exploration of coordinate systems and discuss a coordinate system that is super useful when the pattern may seem or appear to be very chaotic or doesn't exhibit some typical pattern that you can easily recognize, and that's sometimes referred to as parametric coordinate systems. So let's assume that we have a particle that's sort of moving in a Cartesian space, in particular two-dimensional, just to keep things simple. Let's assume that it starts off for somewhere here, and let's assume that it starts off at t is equal to 0 at this particular location, and sort of moves in this particular pattern, and it gets all over here after 1 second. Let's assume that it gets over here at time t is equal to 2 seconds. Let's also keep track of the direction for which this particle is moving. So let's just assume it's moving along that path. And let's assume that it travels that path, gets there at t is equal to 3, in particular in that particular orientation. And let's assume that at t is equal to 4, it gets back there again, right? So, and let's assume that it sort of follows the same exact path forever, which means that the path of this particular particle follows a periodic pattern with a period of 4 seconds, right? So obviously the x-coordinate is following some particular function of time, and y of t is also following some particular function of time. Let's assume that those functions of time are f and g. If you can find f and find g, then what you have here is that the coordinate value x of y is actually a parametric version of some parameter t, right? So this is what we call Cartesian coordinate systems, and this is what we refer to as parametric coordinate systems, where the parameter, in this case, is t, which is going to be standing for time. So that's the main notion of parametric coordinate systems. The only hard part usually when observing some pattern is actually finding a closed form representation for the function f and g, which most of the time does not exist. But if the behavior and movement is simplicial, usually that characterization of f and g are actually quite easy to understand. So let's actually go through a few basic examples of where the function f and g are actually pretty straightforward. Let's start off with the parametric function x of t is equal to 2t, y of t is equal to 5t, and let's assume that our parameter t ranges from 0 to infinity. So what does this parametric function, which of course requires two elements to graph, an x component and a y component, both with respect to our parameter t, look like? Right? So what we can easily do is plot in a bunch of values for t and just plot those xy coordinates. So when t is equal to 0, notice that we have the point 2 times 0, which is 0, and y is actually always equal to 5. So at time t is equal to 0, we're at this particular point here. When t is equal to 1, notice that we're at the point 2 times 1, which is 2, again at 5, right? So one can show that we actually have all the points in between that point and that point. Here this is 2, 5, and this is the point 0, 5. One can show that after another second, let's say, at time t is equal to 2, it's going to be here at the point 4, 5, and actually what you'll see is that this is pretty much what we have, right? So in the Cartesian world, this is actually the function f of x is equal to 5 with domain x is greater than or equal to 0, right? The only difference is we could change the speed for which we traverse across this ray or a line segment where one end goes to infinity by changing that rate parameter into 3 or 5. The function representation would be the same in the Cartesian world, but the speed for which we traverse across it is dramatically different. So although you can convert between parametric and Cartesian coordinates with ease, because in some sense x and y are the Cartesian representations, they just might change in a non-functional way, parametric functions actually tell you a little bit more. In particular, it tells you the speed for which you traverse along a curve, where Cartesian functions don't necessarily tell you those types of things. All right. So every time you're graphing parametric curves, you must always keep track of the direction for which you're traversing along curves, and you might also need to keep in mind the x and y values and the t values that generates those particular locations. All right. So those are just some of the basics you need to keep in mind when graphing parametric curves. So let's just do another example just to make sure we understand. So let's assume x changes with respect to the function 2t minus 3. And let's assume that yt changes with respect to the relation 3t minus 5. And let's again assume that the domain of our parameter t is from 0 to infinity, and we can think of t to represent time in this case. So what we can do just to keep things pretty simple is to create a table of values. For example, we can march across our time domain, and then we're going to have our output values x and y. Right? So let's assume that t ranges from, let's say, 0, 1, 2, 3, 4 continuously. And let's see what those associated x and y values are going to come out to. So when t is equal to 0, notice that our x value is going to come out to minus 3 and our y value is going to come out to minus 5. When t is equal to 1, that's going to give us 2 minus 3, which is minus 1. When t is equal to 1, that's going to give us 3 minus 5, which is minus 2. And notice that in this particular case, our change in x is going to be positive 2, and our change in y is going to be equal to positive 3. Right? So notice that these numbers, sort of like they did in Cartesian functions, sort of represent slope, but they don't represent slope with change to y and also x, but they represent slope with respect to time, right? So in some sense, you can say that delta y with respect to t is equal to 3, and delta x with respect to time is equal to 2. Right? So those are very important things to keep in mind, especially if you plan on going to single variable calculus, where the study of change is actually very, very important. So using that notation, we can just plus 2 and plus 2 to get 1 and 3, and also 5 for other values. And then we can plus 3, plus 3, plus 3 to get other values, so we can get 1, 4, and 7 to get those values there. Once we have those particular values, then we can sort of see, okay, well, that gives us some particular graph, right? So what would that particular graph look like? So if we sort of graph that out, what we're going to have is we're going to have our starting point, or our initial point, which is minus 3, minus 5, located there. So minus 3, minus 5. So that's our initial point, and then it's going to traverse along this particular direction, right? So we have minus 1, minus 2, so that's our t is equal to 1. We have our point 1, 1, let's assume, which is located there, so that's t is equal to 2, and then we have t is equal to 3, and that goes on to infinity to infinity. So again, this is an equation of a ray, but that gives us, a different relation, right? So is it possible that we can find the actual Cartesian representation of this curve? Obviously, because this is a line, but the slope of that line, m, which is typically given by delta y divided by delta x, is not really obvious. But notice that we can find delta y over delta x by doing delta y over delta t divided by delta y over delta x, right? So, or delta x over delta t. Let's write that a little bit more clear. So delta y over delta t and delta x over delta t, right? Because notice that our delta t's cancel, so delta y delta t is equal to 3 and delta x over delta t is equal to 2, right? So that gives us 3 over 2, and then we just need to figure out what that vertical intercept is in order to find, what our b, or our vertical intercept, would be. Right? And obviously the domain of that function would be equal to minus 3 because it's definitely increasing in terms of our x components. So it would be actually, in this case, very easy to convert to Cartesian form with a respective domain, of course, right? But that's just some things that we can observe very easily with that example. Another example that is actually quite interesting, x of t is equal to cosine of t, and y of t is equal to the sine of t, right? And keep in mind, this should ring a bell because this is just 1 cosine t and 1 sine t. So x is equal to r cosine of a parameter and y is equal to r times the sine of a parameter. So you should remember that this is actually the equation of a circle, right? And in particular, we can take our t to belong to the interval 0 to 2 pi, and let's keep that open so it doesn't sort of overlap. So what type of graph will this have? So this again will be the graph of a circle. But keep in mind, it's not just the graph of a circle because parametric coordinates keep track of a few other things: where we start, where we end, the orientation, and the rate of progression along that particular curve, right? So keep in mind when t is equal to 0, xy is equal to 0 over 0. So that's our initial point, t is equal to 0. And one can verify that this parametrization of this curve will traverse counterclockwise until we get all the way up to right before that point, which is going to be located at exactly 2 pi, where those points will overlap. Right? So those are just some basic functions and curves you should know when plotting parametric points and parametric coordinate systems. Again, it's very important when graphing parametric curves, always sketch the curve and at least the orientation that that curve is being traversed. Just like Cartesian and polar functions, there's several other functions that are sort of special in the parametric world. One of them is called the Lissajous curves. So the Lissajous curves are given by the parametrization x of t is equal to a times the sine of little a t plus b, and y of t is equal to capital B times sine of little b t, or let's call it ct, plus d. Some people will define this by letting d be equal to 0, but in terms of parallel structure, one could define it in this way if they desire. So what do the Lissajous curves actually look like? Let's look at a couple examples. So let's start off with some basics. X of t is equal to the sine of t, and y of t is equal to the sine of t. Right? So keep in mind, sine of t is always between -1 and 1, and that's true for all t. And obviously that's the same exact function, so that's also going to belong to -1 to 1 for all values of t. Right? So if it's between -1 and 1, also notice that for all t, x of t and y of t are always equal to each other, right? So that's going to correspond to y equals x in the Cartesian realm. So if we were to graph this particular relation, what would it look like in the xy world? So obviously, we're going to have y is equal to x, but the values are only going to range from -1 to 1. Right? So in this particular case, if this is one endpoint and this is one endpoint, this will be the graph of your parametric curve, the pink line only, right? So in this particular case, if we are going to be taking our domain parameter t to belong to -infinity, infinity, this point is going to correspond to t is equal to -infinity. This point is going to belong to t is equal to positive infinity, and one can verify that it's going to traverse in the upwards direction. So that would be an extreme case of a Lissajous curve. In particular, this is a Lissajous curve with parameter a is equal to b is equal to 1, little b is equal to little d is equal to 0, and little a equal to little c is equal to 1. Right? So by definition, it is a Lissajous curve, although it doesn't really have any curviness to it. Right? So let's look at another variation of this, a slight variation. Let's look at x of t is equal to the sine of little t plus 1, and y of t is equal to sine of little t. Right? So capital A, capital B, both 1, little a, little c, both equal to 1, little b equal to 1, and little d being equal to 0. So by definition, this is also going to be a Lissajous curve. Right? So one can plug in a bunch of values of t and then obtain the corresponding values of sine of t plus 1 and t, what you're going to get when t is equal to 0, we're going to have the sine of 1. And the y of I is going to be the sine of 0, which is 0. So this is going to correspond to your t is equal to 0 point. And what you're going to have is you're going to have actually a little axis that's sort of tilted by. And what we're going to have is we're going to be rotating about that curve in this particular way, right? So we're going to be traversing along this elliptical pattern until we get back to there, right? So what are some other special points in this particular picture? So if we assume that the domain for this is going to be t belongs to 0 to 2 pi, what you actually have here is that pi is going to correspond to that point, and then you're going to obtain all the other points in this particular graph, and I can let you sort of explore, for example, what value gives you that and what value gives you that in terms of the value of t. Right? So a couple other variations of this, slight variations at least. So let's look at example 3. Let's assume it's t plus 2 instead of t plus 1. So x of t is equal to the sine of t plus 2, and y of t is equal to the sine of t again. And let's assume that, again, t belongs to the interval 0 to 2 pi. You're actually going to get a very similar graph, except that that line is actually going to go in a different direction. But as usual, when t is equal to 0, you just get a point that's a little bit more farther out. That's going to be the sine of 2. So t is equal to 0 still starts there, but instead we're going to be rotating in this particular direction, right? And we're going to be orienting in this particular way. At least one special point that you probably can guess is going to be this point right here. That's going to correspond to t is equal to pi, and then t is equal to 2 pi is going to put us back exactly where we started. Right, so quite interesting. So we have easily the graphs of ellipses in parametric form, which you can probably get in the realm of polar coordinates very easily as well. So let's give another example of a Lissajous curve that's actually pretty interesting to look at. So let's do x of t is equal to the sine of 2t. Let y of t be equal to the sine of 1t. And let's assume again that t belongs to the interval 0 to 2 pi. So this Lissajous curve is actually quite interesting to look at. So when t is equal to 0, notice that both x and y are both going to be equal to 0. So t is equal to 0 is going to be corresponding to this point right here. And as you traverse along t from 0 to pi, what you're actually going to get is this particular curve. Let's see if I can graph it with respect to the geometry that it actually has. So this is almost a flat line on the top, but it's actually not. And then we're going to sweep back down and sort of do a mirror image for that. And we're going to be traversing in that particular direction, right? So once you sort of rotate around that particular point, that's going to be equal to t is equal to pi. And then as you sort of rotate around this particular point, that's going to be equal to t is equal to 2 pi, which is going to put you sort of back where you started. All right. Now, what happens when we sort of switch our location of our 2? So what happens when we have, for example, x of t is equal to the sine of 1t, and y of t is going to be equal to the sine of 2t. And let's assume that we take the same exact domain, 0 to 2 pi. The graph actually is not going to change dramatically, aside from a quick rotation, right? But just as before, when t is equal to 0, both x and y are equal to 0, so we're still going to be starting at the origin here, right? So that's still going to be t is equal to 0. But instead of t is equal to 0, what we're going to be doing is we're going to be rotating in this particular direction. So we're going to be rotating in this direction, right? So once you sort of reach here, that's going to be t is equal to pi. And then we're going to be continuing to rotate in this particular direction into that particular point where we sort of started, right? So this particular point here, once we reach that, that's going to be t is equal to 2 pi back where we started. So it's the same exact graph as before, except it's sort of rotated 90 degrees with a slight inversion on its direction, right? So that's actually pretty interesting. So if we sort of add 1 to the domain of one of these t's, sort of like we did before, where we had this sort of elliptical fashion, what you're going to have is sort of like a skewed figure 8 looking thing like we had in example 4 and 5, which is actually pretty interesting to look at. So if we consider the Lissajous curve, x of t is equal to the sine of 2t plus 1, and then letting y of t be equal to just the sine of little t, what you're going to have is, again, a very interesting structure. So again, we're going to have our x-axis here and our y-axis here. So when t is equal to 0, we're going to have sine of 1 comma 0 as our starting point. So we're going to be located somewhere over here, right? So that's going to be t is equal to 0. And what we're going to have is we're going to sort of work backwards a little bit. And then we're going to sort of come up and try to do a little elliptical pattern. And then we're going to approach that particular point again, right? So once we sort of sweep in to that particular point, that's going to approach t is equal to pi once we pass that intersection. And then once we pass through that point, we're going to be sweeping past it and then going downwards and then back up, right? And those should be symmetrical curves, right? In particular, that point and that point are equal but opposites, and that point and that point will be equal but opposites as well, where they have the same exact x value, let's assume. Right, so once we sort of sweep in that particular direction, that's going to give you t is equal to 2 pi, and then it's going to sort of go along that sort of skewed 2-orbit elliptical pattern along that particular curve, right? So Lissajous curves gives you lots of varieties. Obviously, you can use some parametric graphers to sort of look at other Lissajous curves and their variations. I'm not going to go through, for example, sine of 3t, sine of 4t. You'll get a lot more different orbits in that Lissajous curve, so I definitely strongly recommend you looking at some computer software to look at those Lissajous curves because they are definitely some interesting shapes. There's lots of different ways you can extend and generalize parametric coordinate systems, and one of the most common ways, especially in computer graphics, is associated to k-simplices or k-simplexes, depending on how you prefer to pronounce it, and also barycentric coordinates, which have several different applications in computational geometry, which we won't get into here, but I'll give you some of the basics that you definitely should know in case you're curious on going into, say, computational geometry or computer graphics or anything of the sort. So, just a couple of basic definitions to sort of get us underway for this. A k-simplex is going to be a k-dimensional polytope, which is just a convex hull of its k plus 1 vertices, right? So a k-simplex has k plus 1 vertices. That's the first thing to keep in the back of your mind. Also, it is going to be a convex hull of its k plus 1 vertices. So maybe you're not familiar with this word convex, so let me just give you a couple examples. So in two-dimensional world, a set is said to be a convex set if you take any 2 points within its interior or its boundary, connect them with a line, traverse across that line, and every point that you get within that traversion is also within that set. So in this particular set, which is graphed in black, notice that all points on that green line are within that set. Now, just because it's true for that particular line doesn't necessarily mean it's true for all, but you should be able to see that if I choose any 2 points, especially on the extreme points of the circle, and connect them with a line, that particular line is going to always be contained within that circle. This has a lot of applications in linear programming and optimization, but we'll get into that at a little bit later time. So an example of a convex set would be particular that. An example of a non-convex set would be this, right? So this is not convex. Because if I were to choose that point and that point, yes, that belongs to the set, but if I were to pick this point and that point there and connect them with a line, notice that there are some points that do not belong within the set, therefore this set is not convex. Right? But keep in mind, these graphs are not polytopes, and a k-simplex needs to be a k-dimensional polytope. And keep in mind, a polytope is one whose edges are straight lines or line segments. So a convex polytope would be something like this quadrilateral, right? So this is a convex polytope. And if I want a non-convex polytope, it would be something like this. So this is a non-convex polytope, right? And you should be able to count the vertices of this as well. For example, 1, 1, 1, so that has 4 vertices, and we have 1, 2, 3, 4, 5 vertices here. Right? So let's get back to the definition of what it means to be a k-simplex, right? Because keep in mind a k-simplex is a k-dimensional polytope with k plus 1 vertices, right? So there are some restrictions on what a k-simplex can be. So if we consider a 0-dimensional simplex, what does a 0 simplex look like? Well, a 0-dimensional simplex is going to have 0 plus 1, which is going to be equal to 1 vertex only. And the only way that a polytope can have one vertex is if that polytope is a point, and a point only. So a 0-dimensional simplex is a point. If we consider the 1-dimensional simplex, which is just k is equal to 1, that means the number of vertices we're going to have is 1 plus 1, which is going to be 2 vertices, right? So a 1 simplex will be a line segment, right? And if we consider anything above, for example, a 2-dimensional simplex, which is just k is equal to 2, that's going to give us 2 plus 1, which is going to be 3 vertices, and a 3 vertice simplex, that is a polytope and convex, is going to be a triangle, right? So a 2 simplex is a triangle, a 1 simplex is a line segment, a 0 simplex is going to be a point, a 3 simplex would be a tetrahedron, and that would of course extend into higher dimensions, but we're just going to be primarily focused on the 2 simplex here, right? So triangle and a 2 simplex are going to be synonymous as far as we are concerned. So now that we know what a simplex is, now let's talk about barycentric coordinates. So a barycentric coordinate system is just a coordinate system such that the locations of a point are specified with respect to a simplex. So if we consider one of the more simpler simplices, in particular a 1 simplex, which keep in mind a 1 simplex is just a line segment, and let's assume that our line segment looks like this. Let's pretend that it's not embedded in 2 dimensions, even though it technically is on this particular graph, but it technically is a 1-dimensional object. So since we have a 1 simplex, that makes it a line segment, and that means it has 1 plus 1 vertices, right? So that means this is vertex 1, and let's this be vertex 2, and let's assume that is the case. So what we're going to do in terms of the definition of barycentric coordinates is we're going to define vertex vk to be equal to 0, 0, 0 down to 1, and then 0, 0 down to 0 everywhere else, where this represents the kth position of this k-dimensional vector. All right, so that means v1 is going to be equivalent to the point 1, 0, and that means v2 is going to be equivalent to the point 0, 1. Regardless of where this line segment is, for example, I can draw this line segment this way. For example, I can just move this point v1 over here, and I can move this point v2 down to here. That still is the point 1, 0, and that still is the point 0, 1. So although they are located in different spatial locations in R2, they are still the same locations with respect to the simplex. In particular, it just tells you the distance you are from vertex 1 and also vertex 2. Right? So in terms of traversing across this simplex, in terms of barycentric coordinates, what we're going to be doing is we can traverse in either the direction from v1 to v2 or from v2 to v1 if you really desire it. Right? So all points between v1 and v2 will also have a location. Let's, for example, say xy, that is going to have the property that x plus y will always be equal to 1, regardless of where you are located in that picture. So if that is the requirement for barycentric coordinates, where in terms of the values of x and y being bounded above by 1, bounded below by 0, and such that the sum of all n-tuple values is equal to 1, then what would those values be equal to? So if I were to take a particular line segment, for example, and I were to say, consider this to be V1, this to be V2, and let's again say that that's 1, 0, and let's assume that it's 0, 1, and let's assume that this point is the midpoint of that line segment. That means we're half of the way from V1 and half of the way to V2 if you're traversing in that direction. In this particular case, for this particular point, notice that we're really close to V1, a quarter of the way from V1, and then we're 3/4 away from V2. And this, we're 3/4 away from V1 and 1/4 away from V2. Right? And notice how I'm sort of reading that out, even though it's not matching what I'm writing, because this is the same thing as 1 minus a quarter to a quarter, or you can view it as 3/4 and then 1 minus 3/4. Either way is probably perfectly okay, but I think the first one is a little bit more natural to read. Right? So that's pretty much what we're looking at here in terms of barycentric coordinates. It just tells you the distance from one point to another. Right? So let's actually look at an applied problem to sort of see if we can convert from Cartesian coordinate systems to maybe barycentric coordinate system by sort of embedding a one-dimensional simplex into a two-dimensional world. So let me just take a moment and write this problem out for you. So consider one simplex that has been embedded inside of our two-dimensional space R2 with Cartesian endpoints V1, which is characterized by -3, 5, and the other vertex V2 characterized by the location 2, 8. What point xy in R2 would be associated to the barycentric coordinate 0 0.3, 0 0.7? So what is exactly this problem talking about? So let's just draw a picture. So what we have here is some vertex V1 that's located in R2, and some other vertex v2 that's also located in R2. In particular, this is -3, 5 in xy coordinates, and this is 2, 8 in xy coordinates. So what we are looking for here is some point in R2, right? So let's assume that this is our point P that we're looking for, also in R2, right? Such that the distance from P is just 30%, and the distance from V2 is 70%, right? So that means we're really far from our V1 and we're really close to our V2 point, right? So what exactly does that mean? So that means this distance here in terms of the total distance. So what would the total distance between these 2 points be? So let's just find that. So the distance from V1 and V2 in Cartesian world, that's just going to be equal to the square root of x sub 2 minus x sub 1. So -3 minus 2 the quantity squared plus 5 minus 8 the quantity squared. So that's going to be the square root of 25 plus 9, and that's going to be equal to the square root of 34. Right? So if that is the case, so we want to represent this in barycentric coordinates, which is 0 0.3 and 0 0.7, that means that this point, again, is equivalent to 1 minus 0 0.7 and 0 0.7, right? So actually this point should be closer, if I were to draw this to scale, somewhere located there, right? So that's pretty much what we're looking at here. So this point is P, 1 minus 0.7, 0.7, and equivalent to some point xy in Cartesian space, right? So let's just redraw our lines so it looks sort of accurate. So that means this distance here is going to be 70% of the distance, and this distance here is going to be 30% of the distance, where the entire distance from here to here is just going to be equal to d. So what points will make that true? Also keep in mind, since we are embedded in R2, we can find the slope of that line segment, right? So the slope of the line segment passing through V1 and V2 is going to be equal to what? So it's going to be equal to y2 minus y1 all over x2 minus x1. So that's just going to be equal to 3 divided by 5, right? So that's the total distance, the square root of 34, and that's going to be the slope between these two particular points. Agreed? So that gives us some things to work with here. So what we're going to do is we're going to look at a couple very interesting things, because what we're looking for is this point x, y, right? So if we sort of make a right triangle with respect to P, this distance right here is x, and this distance right here is y. So if we were to be able to find this angle theta, then practically everything else should follow very quickly. Right? So notice that if we use just our basic relations from trigonometry, that the tangent of that angle theta is going to be to the opposite side over the adjacent side, right? And again, we do not necessarily know what y over x is, or do we? But keep in mind that the tangent of y over x, regardless of what y over x is, if it's with respect to the point 0, 0, that actually is going to be the slope of our line. So the tangent of that angle is always going to be equal to the slope of that line. And that's a very, very interesting thing to keep in the back of your mind if you don't already know it. So using that observation, that means that angle of inclination is always going to be equal to the arctangent of the slope of that line segment. All right, so once we have our theta, now we can use some other relations to find out what x is and what y is, because we also know, using right triangle trigonometry, that the cosine of theta is going to be equal to the adjacent value. So the adjacent value, which is going to be x, all over the hypotenuse value, which in this case is going to be 0.7 times d. And we also know that the sine of that angle theta is going to be equal to opposite over that hypotenuse value, which is 0.7 d. Right? So once we have those particular values, we can solve for x and y. So in this case, we're going to have that x is equal to 0.7 times the total distance between v1 and v2 times the cosine of theta, and y will be equal to 0.7d times the sine of that angle theta. All right, let's keep it in parallel structure, shall we? Right? And keep in mind, notice that in some sense this is a parametric equation where our parameter is now theta, which is, also of course similar to polar coordinates as well, except you just have one equation instead of two. Right? So what exactly is theta? Well, theta is equal to the arctangent of our slope, and we know what our slope is. So therefore we can turn this equation into x is equal to 0.7d times the cosine of the arctangent of our slope, and y is going to be equal to 0.7 times the total distance times the sine of the arctangent of our slope. And as long as you're working in radians or degrees, it still should work out. You should be able to find that this is equal to 1.5 and this is equal to 0.9 exactly, right? So that means the point 1.5, 0.9 in Cartesian world is going to be equal to the 0.3, 0.7 V1, V2 barycentric world. So these 2 points are equivalent to one another. Now, a little side trigonometry exercise in case you don't know how to work this out already. Some identities you definitely should be able to prove if you haven't already. In particular, the cosine of the arctangent of m actually has a nice representation in terms of radicals and rationals. That's just 1 over the square root of 1 plus m squared, and also the sine of the arctangent of m. This is equal to m over the square root of 1 plus m squared. So I definitely invite you to try and prove those two results because they are definitely useful, especially once you get to integral calculus a little bit later on. Right, so those are the basics of barycentric coordinates on one simplexes. So what about barycentric coordinates on a two simplex? Right, and keep in mind a two simplex is just a triangle, right? So a two simplex is a two-dimensional polytope whose convex hull lies within that two-dimensional space, and it has 2 plus 1, which is 3 vertices. So that means this particular graph would be a 2 simplex. It has 3 vertices, so we can label them V1, V2, and V3. And by the naming convention from before, that means this is the point 1, 0, 0, this is the point 0, 1, 0, and this is the point 0, 0, and 1. Right? So every point on the boundary of this triangle, and of course the interior, the convex hull of this triangle, can be expressed in terms of locations x, y, z, right? So x, y, z, where the sum of these values, x plus y plus z, x plus y plus z, must be equal to 1, and each of these values, x, y, z, must belong to 0 and 1, inclusive of those boundaries. So just some points that you should know. For example, if this is the midpoint of that side, that's going to be the point 1 half, 1 half, 0. If you take the midpoint of this side over here, midpoint, that's going to be 0, 1 half, 1 half. And if I pick this point down here, midpoint, let's assume, that's going to be equal to 1 half, 0, and 1 half. It's halfway between V1 and V3, and it's not towards V2. Right? And if I connect these points together, so connect those 2 points together, connect those 2 points together, and connect those 2 points together, we get this interesting point there. Some people will call this the centroid of the triangle. And in terms of physics, this is called the center of mass. One can show that this is actually going to be 1/3, 1/3, 1/3 in terms of its coordinate. So it's sort of, halfway in some sense from V2 to V1 to V3. So it's sort of in the center. Right, and that's how you would do barycentric coordinates on a two simplex. Obviously the math is a little bit more involved, but not impossible. And there are also other objects which are called simplicial complexes, or complices, depending on how you pronounce it, which is just a bunch of simplexes unionized together. For example, we can have a two simplex here. We can have another two simplex there that share 2 vertices. We can have another two simplex there. We can have a 0 complex sort of chilling on the outside, and we can have a 1 complex that's sort of hanging out on the edge of one of those 2 complexes where one of those vertices are shared. So that would be what we call a simplicial complex, right? And sometimes they would also assign it a dimension. For example, a k-simplicial complex. K is typically chosen to be the maximum of the simplices that are within that simplicial complex, right? So since triangle is the highest order simplex in that particular complex, this would be a two simplicial complex, right? Several different applications on the theoretical end that one can go through here, but I will not talk about them here. I'll leave them for a later time. So those are some of the basics that you definitely should know with working with parametric coordinates, and also some of those extensions from parametric coordinates into the realm of simplicial complices and also barycentric coordinates. Hope you enjoyed this video, and I'll see you in the next one. Take care.